At 12:28 p.m. on January 2019, 12 million cubic meters of iron ore waste lost its structural cohesion. In exactly 22 seconds, the entire mass unraveled, flowing downward like spilled liquid. Traveling between 70 and 100 kilometers per hour, the mud flow reached the neighboring village of Vila Fartego within seconds. It swallowed the visitor parking lot, the administrative offices, and the cafeteria where workers were eating lunch, killing 270 people. 4 months earlier, this specific structure, Dam I of the Feijao Dam complex, had undergone a formal safety audit. An independent, qualified consultant reviewed the dam's metrics, signed a stability report, and legally certified the structure as stable. Understanding how a certified dam disintegrates without warning requires looking at two intersecting mechanisms. One is the physical behavior of saturated soil. The other is a slow, quiet drift in organizational behavior that takes place entirely on paper. Investigators found that the science of the collapse was already well understood. The complexity of the case lies in how the dam's legal status remained active, even as its physical internal structure reached a breaking point. This cross-section illustrates the upstream method, which is the cheapest way to construct a tailings dam. The operator pours a starter wall at the bottom of a valley and fills the space behind it with tailings, the wet, sandy residue left after iron ore is washed. Once the surface dries, the next lift is built directly on top of the waste. Because it sits on its own waste, the materials inside are dangerous. They are heavy, saturated with water, and highly brittle. In soil mechanics, brittle material behaves in a very specific way. When subjected to the right kind of disturbance, it loses almost all of its shear strength. This leads to a mechanism known as static liquefaction. Liquefaction is typically associated with earthquakes, where intense ground shaking forces water pressure up until the soil behaves like a fluid. Static liquefaction requires no seismic event. It requires only the right water content, the right material, and a slow, almost invisible increase in stress for the mass to lose its strength entirely on its own. Because static liquefaction triggers internally and transforms a heavy, solid structure into a fluid mass in an instant, it does not behave like a typical landslide. The mass unravels from the inside out. Looking closely at the internal structure of the dam, heavy seasonal rains elevated the pore water pressure inside Dam I. Deep within the saturated tailings, a microscopic deformation called creep was taking place. It occurs when materials sit under sustained stress over long periods, concentrating strain near the crest. While this strain built internally, surface equipment recorded deformation of 30 millimeters per year. Operators reviewed this displacement and labeled it expected. Conventional dam instruments are calibrated to detect familiar warning signs, identify external cracking, measure seepage through the wall, or track rapid crust displacement. There were no apparent signs of distress on the morning of the collapse, because the instruments were designed around the assumption that the dam would issue a visible warning before it fell. The sensors were fully operational, but they were looking for the wrong physical signals, leaving the operators blind to a structure that was systematically failing on the inside. To operate legally under international standards, a tailings dam must be reviewed periodically. The standard mandates that under undrained conditions, the dam must possess a minimum factor of safety against failure of 1.3, meaning it can carry 30% more load than the load required to make it slide. When the German auditing firm TÜV SÜD ran the calculations for Dam I in 2018, they did not reach 1.3. The undrained factor of safety they obtained was approximately 1.06. A factor of exactly 1.0 represents the mathematical threshold of imminent collapse. This formula calculates the factor of safety. Faced with a 1.06, an engineer can refuse to certify the dam. Instead, the Brazilian auditing team tested alternative calculation methods within this equation. They selected different assumptions for the strength parameters of the tailings. They adjusted the mathematical inputs for drainage and pore pressure until the final output passed the required minimum. This reflects the normalization of deviance. It is a slow organizational drift where strict rules are gradually replaced by rules with exceptions. A 1.06 factor of safety is rounded into existence through a long chain of choices, each one individually small and defensible on paper. The resulting safety review from September 2018 managed to say two things at once. It formally declared the dam stable, providing the legal trigger for the mine to keep operating. Yet the same review included a list of strict recommended measures: avoid vibration near the structure, prohibit nearby detonations, and avoid heavy equipment traffic on the dam itself. The legal signature created a perfectly safe dam in the documentary record. It allowed daily operations to continue at the base of a physical structure that the auditors explicitly warned should not be disturbed. Static liquefaction in upstream tailings was not a new discovery in 2019. It was a known, heavily documented mechanism in the geotechnical profession for decades. 3 years prior, the same parent company, Vale, was involved in the failure of the Feijao Dam at Mariana. That collapse killed 19 people and discharged 43 million cubic meters of tailings into the surrounding river systems. The lessons from the Mariana failure were thoroughly investigated, written up in expert panel reports, and published. They were readily available to the engineers evaluating Dam I, yet none of those physical realities were reflected in the calculation that produced the 1.06 safety factor. When the people choosing the mathematical assumptions are paid by the operator they are auditing, the integrity of the process degrades. Engineering science cannot protect the public when the certification process is intentionally detached from the physical evidence. The regulatory and financial consequences arrived in waves. The United States Securities and Exchange Commission filed a civil complaint explicitly alleging that the audits were, quote, corrupted by the purposeful use of unreliable data. Brazilian authorities filed charges against 16 individuals, and Vale lost the equivalent of $19 billion in market capitalization in a single trading day. Comparing the abstract math of a factor of safety against the weight of 12 million cubic meters of brittle rock highlights the gap between engineering theory and its professional application. The lesson for the geotechnical profession is that the documentary chain of safety, the periodic review, the auditor's signature, the regulator's filing, can be successfully engineered to point in a direction that simply does not match the physical state of the structure. A factor of safety is just a number. It can be recalculated, adjusted, and rounded, but it cannot suspend the laws of soil mechanics. The dam collapsed because a small set of human choices placed a signed piece of paper between a critically unstable structure and the people working directly downstream.